Welcome! In this lecture, we will talk about battery sizing principles. We will focus on the range aspects for the car and take a look inside QSS on an electric vehicle model. First of all, we have an energy demand for our drive cycle. We all know that energy is equal to the integral of power over time. Ts defines the start time of the drive cycle, and Tf is the final time. In QSS, the power needed is the input to the battery. Typically, a few constraints are valid for the battery. We will look in QSS later how the energy can be calculated. Also, the battery contains energy, of course. E cell denotes the energy content in each cell. Typical energy level for a cell varies, of course, depending on cell chemistry and which type of application. High energy density or high power density. But assume for now that the value of 100 watt-hours is a common cell. NS denotes the number of cells in series connected, and NP is the number of strings parallel connected. Let's dig in deeper to the number of cells in series. Cells connected in series creates together a higher voltage potential for the battery pack. How do we determine the number of cells connected in series then? Well, the DC link voltage is decided by the electrical motor and other consumers. In principle, a higher DC link voltage, U0 in the picture, will provide a higher efficiency for the consumers. And overall, this will lead to lower losses. And then that will result in less consumed energy. But we also need to have a voltage high enough in order to be able to switch the electrical motor and form a proper PWM wave. PWM stands for pulse width modulation. If the voltage is too low, we will need to add another DC-DC boost converter to raise the DC link voltage, which then introduces additional losses and costs. A common voltage level today is 400 volts on the DC link. The upper limit of DC voltage is limited by the isolation class of the components. Consider if each cell has an open circuit voltage of 4 volts, we need to have at least 100 cells connected in series to obtain the desired voltage level. Let's keep this in mind for QSS later. NP is the number of cells in parallel. In general, if we have already decided the DC link voltage level and we need to add more energy content in the battery, one option is to add more parallel connected strings. Consider that we have 100 cells in series, each with 100 watt-hour capacity, and we have one string. This will be equal to 10 kilowatt-hours, which is a battery size in comparison to a plug-in hybrid today. Two strings, parallel connected, have similar energy level as a Volvo C30 electric produced 2011, which is around 20 kilowatt-hours, or 24 as the C30 electric had. If we have 4 strings, parallel connected, the energy content will be similar to a Renault Zoe with 41 kilowatt-hour battery, or new generation Nissan Leaf, 40 kilowatt-hour of energy. Adding up to 5 strings will have the energy content as a GM Volt. Adding even more strings, parallel connected, up to 9, will be a level of Tesla Model S, which will be 90 kilowatt-hours. This was a short introduction to battery scaling and characteristics. Now let's take a look inside QSS and the battery model. Remember the properties we have discussed? series connected cells, parallel connected cells, battery energy, and energy need in the drive cycle. Here we have a Simulink model that contains QSS blocks. I have implemented a conventional powertrain and an electric powertrain. To the left, we have the drive cycle, and the electric powertrain contains of a single gear ratio and an electric motor. The output from the electric motor is the power demand. And the power demand also acts as the input to the battery. If we run the model, we will look at the power demand. This is the power needed to propel the car forward. The peak power demand during any DC is about 60 kilowatts. If we recall from the lecture, the energy need during the drive cycle is the integral of the power from the start time to the final time. I have implemented an integrator block in the simulation model as well. Here we have the integrator block, and here we have the time. Together they define the total energy need during the drive cycle. And for any DC and this conventional drivetrain, we have about 2.5 kilowatt hour of energy demand. Let's look into the battery model. The input is the power demand. Then, depending on the cell configuration, we calculate the current for each cell. From the current on each cell, we get the power loss and the output voltage, and also a state of charge. If we have the total distance of the drive cycle, we can also calculate the energy consumption per kilometer. That will determine how efficient the drivetrain is. Let's look at the parameter settings of the battery. We talked about number of cells in series and number of cells in parallel. Together, they will define the energy content of the battery. In this case, 100 times 3 and 100 watt hours per cell will be 30 kilowatt hours. We also need to input initial state of charge. In this case, it's set as 77. Remember that the energy need for the drive cycle was about 2.5 kilowatt hours. And the total energy we have to utilize in this battery is 30 kilowatt hours. Let's look at the state of charge output after we have been running a simulation. We initialize the model at 77%, and we will end up with 73%. When the state of charge goes positive is due to the regenerative braking, which electric cars are able to do. The output from the conventional powertrain is to use a fuel tank, and the consumption figure will be presented as liter per 100 kilometer. For the battery, we will have something called energy consumption, and it will be presented as kilowatt hours per 100 kilometer. In this particular case, 23 kilowatt hours per 100 kilometer. This was the important aspects of the battery model in QSS: the power demand input, the driven distance input, and the parameter settings: number of cells in series, number of cells in parallel, and initial state of charge. Thank you. That was all for this lecture.